Gentlemen, we are so glad to welcome everyone from all over the world to join this youth talks every Tuesday. So today we're going to have a big session for the light, the metal materials. This is Alice from Peking University. Warm greetings for everyone. I'm thinking today we're going to have such a hot topic, as for the metal optics recently development and applications. So I have three super young scientists, to join this session and to, tell us the latest, development. So our first speaker is Professor Yuanmu from Tsinghua University. Yuanmu Yang, I know Yuanmu a few years ago, he delivered a wonderful talks on I Can X that time, and talk about a super story. And Yuanmu was graduated from Cheng University, and then he got a PhD in U.S. And after a few years stay in the U.S., he go back to China to Tsinghua University as an assistant professor. Now he already associate professor. Congratulations. Yuanmu published many high-cited, publication in the high-cited journals. Yuanmu also was very active in this society. So Yuanmu, without further ado, the stage is yours, please.
All right, so let me share the screen first. Okay, so can you see my screen clearly?
Yes, very beautiful. Please.
Okay, it's my great honor to be here, and thank Alice for this very kind and generous introduction. So it's my also my great pleasure to join Howard and Pinji today in this special volume of ICANX Young's talk on meta-optics. Okay, so remember about almost 3 years ago, okay, I gave a talk on this ICANX platform, and today, this time I hope to share something new and hopefully exciting for the broad audience of this entire ICANX community. Okay. So today my topic is going to be how are we trying to use this concept of Metasurface to build a monocular camera with very tiny system form factor for application towards this single shot and multi-dimensional imaging. Okay. And this work has been done by my fantastic students and postdocs, including Feng, Zicheng, Yibo, Liu Shuai, among many others. Okay. So today I'm just presenting on behalf of them. Okay. Now to start with, I want to just show something simple. Okay. This is the camera that now everybody uses in their daily life, right? So for a conventional camera, we know that we have the target object and an optical system that's often composed of a few pieces of lenses. Okay, then we have a CCD or a CMOS sensor for record all the information. Okay. Whenever you take a picture, this is something you may get, right? So this is a 2D intensity image that sometimes comes with a mixture of red, blue, and green colors. Okay. But in the meantime, actually, we are also losing a lot of important information. Okay. For example, for a conventional camera, okay, it doesn't have this depth information of the thing. Okay. And also, if you remember that light is actually an electromagnetic wave, so it has carries a lot of information such as the phase, polarization, and spectrum. Okay, and all those information are actually are lost when you capture this image. Okay, so the next question becomes, why do we care? Okay, so it is actually highly desirable to record this multidimensional light field. Okay, and for example, if you can achieve or obtain this depth information that can help you do this biometric identification. Okay. This is actually how, for example, you do face unlock with your iPhones, right? Also, for those robots and autonomous driving vehicles, you need those 3D or depth information for this spatial localization and mapping. Okay. In addition, if you can get this face information, that can be critical for surface metrology in semiconductor processing. And also it can be very, very useful in biomedical research. That is because, for example, most of our living cells are actually quite transparent and absorbs a very little light. So you need this additional phase information in order to visualize those transparent objects. Okay, and the same goes for polarization imaging and spectral imaging, because you can use those for image enhancements and this image deblur, or using applications such as remote sensing and food or plant analysis. Okay. But what is the problem there? Okay, so I will say that it is not impossible to obtain those extra information. However, to obtain those extra information, okay, the camera typically becomes very bulky and expensive. Okay. For instance, if you want to do this depth imaging in your autonomous driving vehicles, okay, typically these days people now use something called LiDAR. Okay, LiDAR actually is composed of multiple laser heads, some scanning units, and some very sensitive single photon photo detectors. Okay, so the entire LiDAR unit can cost up to a few thousands of US dollars. It's still very expensive up to today. Okay. Also, you may be able to, for example, use this binocular camera, okay, using this triangulation or this stereo vision in order to detect this depth information. However, for a binocular system, okay, the depth estimation range and accuracy is dependent on the distance between these two cameras, or sometimes we call this the baseline between these two cameras. Okay, so that it's really difficult to try to minimize the entire system form factor. Also, for face imaging, nowadays, a typical face imaging system relies on an interferometric setup. Okay, for example, using this white light interferometer or this digital holography system. Okay, it can be quite bulky, and also can be quite sensitive to environmental vibrations. Okay, and for polarization imaging and spectral imaging, okay, typically you need to oftentimes you need to take multiple pictures in order to get this additional information, or the system can still be very bulky. With that, so an overreaching question that we have been asking over the past few years has been that why cannot we use a conventional monocular camera for this multidimensional imaging? Okay. And to address that question, the first thing we did was trying to use a mathematical image information model to try to model how a conventional system it takes an image. Okay. So in a conventional camera, okay, the two-dimensional image that is obtained on this photo sensor, you can treat it as the convolution between your object function and the point square function, or this PSF of your optical system. Okay. So what does this PSF mean? Okay. It actually means basically the impulse response of your optical system with respect to a point light source. Okay. So for example, when you want to take a picture of this black square, the point source, typically a optical system, the PSF for a point light source looks like this area pattern. Okay. So the convolution between this black square and this area pattern will result in something blurry. Okay. So every time when you take out your smartphone and take a picture, okay, the first thing you do is you focus at a certain depth, okay, or at a certain depth point. At that point, what you are actually doing is you are trying to minimize this point square function to a delta function such that you can get a clear and sharp image. Okay. However, in a typical camera, okay, the PSF that is generated by this refractive lens is a single channel 2D function. What I mean by that is that this PSF is optimized only for a certain depth of field and is independent of the polarization and spectrum of the target object. As a result, what you will get is simply a 2D image that is clear and sharp only within this depth of field, and you have no polarization or spectral information, right? So how do we take a multidimensional image with a monocular camera? Okay. And our approach to address this problem is to try to use this coated aperture or this metasurface to replace conventional refractive lens. Okay. What's cool about this coated aperture is that it can generate a PSF that has multiple channels. For example, we can make the point square function of the optical system using this coated aperture to make it to be highly dependent on the depth and the wavelength and the polarization of your target film. Okay. With that, the convolution between this target object and the point square function will still result in a two-dimensional image. But in this two-dimensional image, it will encode this multidimensional information. Okay. that gives us this opportunity to try to use this computational reconstruction, either using this iterative algorithm or using this a deep learning-based algorithm, right, to decode this multidimensional information, including this 2D depth, 2D intensity, depth, polarization, and spectrum. Okay. However, one of the issues with this coded aperture imaging is that it is actually a rather old idea. Okay, in the beginning, people use this concept for X-ray or gamma ray imaging because in the X-ray or the gamma ray band, people don't have a very good refractive lens there. Okay, later on during the 1980s, people extended this concept for application in the optical domain. Okay, so after such a long time, so how can we use this Metasurface to make this coded aperture imaging system better, right? So what can be new here, and what will be the new applications out there? Okay? To understand that, the first thing I need to explain, since I'm the first one to talk in this session, is that I want to just briefly give my understanding of what is the Metasurface. Okay, so in my perspective, Metasurface is basically just an emerging class of diffractive optical element, or DOE. Okay? But with the difference or the novelty being that it's a planar DOE and it's composed of these sub-wavelength scatterers. Okay? If you want to try to understand the evolution of optical devices, okay, in the beginning, okay, since 700 before Christ, okay, people have been using this refractive optics for imaging for thousands of years, okay. So for this refractive optics, how it works is that it modulates the wavefront of light by modulating the so-called propagation phase. Okay, with that, typically this propagation length or this critical dimension of this refractive lens is typically much greater than the wavelength of light. Okay, and later since 1980s, people have developed this very nice multi-level diffractive optical element. Okay, basically for this diffractive optical element, it can be treated as a phase-wrapped version of this refractive optics. Okay, with that, it actually can become much thinner, typically a much on the order of less than a millimeter thick. Okay, for this multi-level diffractive optical element, despite its being very, very thin, it still relies on the change of the thickness of this diffractive layer in order to modulate the phase of the incident light. Okay, so that it is still a multi-layer structure and cannot be fabricated with a single-step lithography process. Okay. And the concept of a metasurface, actually, I would argue that some of the early concept of metasurface originally emerged in 1990s with some pioneering work by Philippe Lalande and others in France. Okay. And later with a seminal paper by Federico Passo's group at Harvard University, okay, roughly during the about 15 years ago, that the entire field of metasurface really exploded, and people got really excited about this. Okay, so what is the difference between a metasurface and a conventional diffractive optics? Okay, one of the major difference physically is that it modulates the phase not by changing the thickness of this diffractive layer. Instead, it actually modulates the effective refractive index of your material by changing, for example, the fill factor of this nanopillars. Okay, so that it can actually be made of a single layer device with a uniform height here. Okay? And in terms of the critical dimension, both the thickness as well as the spacing between these nanoscatters are both at the subwavelength scale. So it has a very, very fine features. Okay? So why this metasurface can be better or can have unique applications towards a lot of different scenarios. Okay, so here I just try to give three major advantages of metasurface in comparison to a conventional multi-level diffractive optics. Okay, the first thing is that the metasurface can be fabricated with a single-step lithography process. Okay, actually over the past few years, there has been many startup companies around the globe. Okay, such as the Metalens in USA and Newt in Denmark and Metalens and other few startup companies in China. Okay, they're all developing this large-scale and wafer-scale fabrication process for metasurfaces. Okay, and currently they can really do a scalable fabrication of a metasurface at a low cost. So that's actually becoming a reality. Okay. Also, as I mentioned, that the metasurface typically have the sub-wavelength spacing, which means that actually it doesn't have any higher order diffractions. Okay, so that can be used particularly suited for example, this large angle beam steering, as well as if you want to make a meta lens for focusing with a very high numerical aperture. Okay. And last but not least, what I would argue that a very important feature and quite different from conventional diffractive optics is that it can generate this polarization-dependent PSF. Okay? That is because actually, when you design the nanoscatterers, you can make them anisotropic. So they may have a different phase response for different incident polarizations. Okay? And as I will show later, okay, this polarization-dependent PSF is going to be critical for a number of applications I'm going to show today. Okay. So today I'll just use the next about 10 minutes, 10 to 20 minutes to try to basically show 3 examples using this monocular metasurface camera for single-shot multidimensional imaging. Okay. For example, for polarization imaging, for polarization and depth imaging, and complex amplitude imaging. Okay. And the first example of polarization imaging is actually quite straightforward. Okay. Actually, one of the interesting application of polarization imaging, as was described by this seminal paper by Professor Yuan Shechner's group in Israel, okay, it showed that you can use polarization for image deblur. Okay, that is because much of the backscatter light is partially polarized, and most natural object emits light that is unpolarized. Okay, so if you took 2 images of orthogonal polarization, you can actually try to separate this object light from those scattered light, right? And give you an image with a better contrast. However, this field has been hampered by this polarization imaging hardwares. Okay, they typically have a limited imaging speed, system form factor, and transmission efficiency. So that here we have been developing this meta lens with this polarization-dependent PSF, okay, that can function as a that can do 2 functions together. Okay, for example, this polarization splitting and focus. Okay, so with one object, and we can form 2 images at the same photosensor, one with X polarization and another with Y polarization. Okay, and in the experiment, we tried to took an image of an LED array using this meta lens integrated CCD camera. Okay, if you put a polarizer in front of this camera, we will see 2 replicas of this LED arrays with a polarization extinction ratio greater than 100 to 1, which is quite nice. And also we have a quite high diffraction efficiency of this meta lens, greater than 51%. Okay. If you consider a polarizer-based polarization camera, the upper limit of this transmission efficiency is only 50%. Okay, so actually this is actually not a too bad number. Okay, so this entire system can do this real-time polarization imaging with a compact system form factor with relatively high efficiency that can be further improved. Okay, with that we try to demonstrate a funny application, that is we try to take an image of this toy shark through milky water. Okay, so you know that in this experiment that we actually used a grayscale image of a toy shark and a black and white image of some kind of a fish. Okay, and we use this measurement of enhancement to describe the quality of the image. Okay, as you can see from the obtained image that doesn't have this any computational reconstruction, you will see that basically these images are quite blurry and has a very low contrast. However, by applying this polarization recovery algorithm, we have a much improved image contrast up to roughly 10 times. Okay. This is the example that we can use polarization imaging for some useful applications, and that also utilize this metasurface and to get a monocular compact polarization camera. But that is still quite simple. Now, next we want to do something more complicated, and let's say, how can we make it more useful, for example, to simultaneously get this depth information of this thing. Okay, to do that, it follows the identical approach, but this time we want to make the point square function not only dependent on the polarization, but also on the depth of the target object. Okay, so in this case, we design our point square function to be this single helix PSF pair. What does that mean? That we design the point square function in such a way that as we change the object distance, okay, and the point square function actually rotates around the geometric center. And for x and y polarization, they are offset by 180 degrees. Okay, we can actually design this very strange 3D point square function using an approach similar to designing 3D holography. Okay, you can refer to this paper here. And how this depth-dependent point square function can be used for depth estimation, I'm going to use this animation to illustrate. Okay, for example, if we have a letter T sitting at a distance of V1, okay, that will form two polarization images that are slightly offset. As we change the distance of the object, you'll see that these two polarization images are going to rotate with respect to each other. Okay, and this rotation angle is going to correspond to the depth of the object, so that if you can measure this rotation angle, that can give you the depth information. Okay, and all this measurement can be done in a single shot. Next, we actually fabricated this metasurface of millimeter aperture using these silicon nanopillars, and we measured the depth-dependent point square function of the fabricated metasurface. It's highly consistent with our design. Okay. And with that, we integrate this metasurface and CMOS image sensor to form the molecular metasurface camera assembly. And we found that indeed, this molecular metasurface camera can capture 4D image, including this 2D all-in-focus intensity polarization, as well as the depth of this target scene, all in a single shot. Okay, you know, this polarization can actually help you to do this material texture recognition, and also this obtain the depth information has a very, very high relative accuracy, with the relative accuracy down to even below 1%. Okay. And also we found that this metasurface integrated polarization depth camera can be used under ambient illumination condition. Here we show that under a sunlight illumination, we can use it to shoot videos for dynamic scenes. Okay, so we show that you can measure the distance of these toy cars here, right? And actually, the paper was published in earlier this year. However, our that prototype was done even about 2 years ago in November 2021. Okay, and as we really feel that this kind of concept of a molecular 3D camera can reshape this entire field of 3D sensing towards a lot of applications. Two of my PhD students and Yibo and Zhen, we actually decided to start this startup company called Waveview Photonics in April 2022. Okay. And within quite a short period, okay, we actually developed the first generation of the molecular 3D camera modules with a much reduced volume on the order of the size of a coin or fingertip, with also a much improved field of view and frame rate. Okay. The first application we targeted is this navigation and collision avoidance of a robot vacuum cleaner. Okay. Now we show that using this molecular 3D camera module, okay, we can have this 3D point cloud with very high spatial resolution, okay, and that can be used for this robot to avoid some obstacles, okay, and the spatial resolution of this device is actually much higher than those commercially available time of flight or those structural light-based systems. Okay, right now we are actually targeting at a relatively short range operation down to about a meter, okay? But we are now also developing a 3D camera module that can see up to tens of meters or hundreds of meters, okay? With that, I'm going to come to my last project, which I think is also quite important scientifically, okay? So we are trying to use the monocular camera for complex amplitude imaging, right? As I earlier mentioned that for a molecular camera system, typically we only get the intensity information of the target thing. Okay? But to remind you that a light wave is actually an electromagnetic wave that contains both its amplitude and its phase information. Okay? So our goal here is trying to actually record this complex amplitude information with some new kind of lens and with some new camera sensors, but still with a very small system form factor here. Okay. And if you look at those conventional measures for a complex amplitude imaging, as I mentioned in the beginning, okay, this interferometric system can be quite bulky. But recently, there has been a lot of work trying to develop compact systems such as this lens-based imaging system or this typography or transport intensity-based approach, trying to also get this complex amplitude or quantitative phase imaging. Okay. However, this system typically they still requires multiple measurements in order to get the phase information, and there may still be this ill-posed problem, so that the accuracy of this phase reconstruction may still needs to be further improved. Okay. And in our work, we use this meta lens for single shot and deterministic complex amplitude imaging. Okay. So here, we basically use a meta lens to generate a spatially multiplex and polarization multiplex point square function. And we also couple that with the polarization camera that can give our 4 channels of polarization images. Together, we actually get 8 different images of this target object. With that, we can actually calculate the phase gradient along both this x and y direction that can give us deterministically this intensity and phase image of this target scene. Okay. Without going into too much details of this mass behind what we call this polarization phase shifted shearing interferometry system. Okay. So if you are interested in the mass, you can refer to this archive preprint that we just posted a few days ago. Okay. Experimentally, that we first show that using this compact complex amplitude imaging camera, we can actually take an image of a transparent UV adhesive. Okay, using an incoherent LED light as an illumination, we can basically get 8 replicas of this UV adhesive sample and get this phase gradient information and get the phase as well as the thickness information. Then we compare our measured phase, the thickness of this UV adhesive with commercial white light interferometers, and we see some very good agreement. Okay, and below I also want to show a video of a dynamic surface metrology using the system. Okay, this the complex amplitude image can be obtained in a single shot. Okay, our system is particularly suitable for observing the dynamic evolution of transparent materials. And the frame rate is only limited by the frame acquisition time of this polarization camera, which is a major benefit in comparison to those interferometric systems. Okay. And in addition, we found that if we couple this meta lens with an objective lens, okay, we can also use it for microscopy applications with much higher magnification. Okay, here we showcase. We took an image of the USAF 1951, a phase resolution target. We also measure its thickness, and show also that it is in close agreement with the measurement of the white light interferometer. Okay. One particular thing that is this entire system is good for that we show that we can use it for label-free observation of paramecium, which is a single-celled organism. Okay, so it's very suitable for the observation of living cells. With that, I hope that over the last 30 minutes, I can have convinced you with these 3 examples. Okay, we can use this Metasurface indeed to build this very compact monocular cameras for single shot multi-dimensional imaging towards a lot of interesting applications. Okay. So with the limited time today, there are still a lot of things I haven't covered what we have done in our lab over the past few years. We have other work on multidimensional imaging, for example, to generate a very large field of view structure light for 3D sensing applications, and also for spectral polarimetries. Okay, and another big section of our research is on nonlinear meta-optics. In fact, one of our work is on a high harmonic generation, which is close related to today's Nobel Prize in Physics, which is on attosecond generation. Okay, so there is a big sectors on this nonlinear optics, which I also have learned a lot from our next speaker, Dr. Howard Lee, right? So I think maybe he will talk a little bit about that as well. Okay, with that, I think I'm running out of my time. And in the end, I just again acknowledge all my students and postdocs, which have done all the hard work, and also our collaborators on the above mentioned 3 projects and all these funding agencies.
Okay, great, Yuanmu. It's a very nice talk. You getting, the time. Exactly. Yeah. So proud of you. Yeah. Actually, as you mentioned that you also done a lot of work for, in the light field, some maybe related with today's Nobel Prize. We can discuss later during the panel discussions. And I will, introduce the second speaker. So our second speaker is Professor Pingjie Wu. Okay, let me share my screen. Yeah, Pingjie was okay. Yeah, already on the screen. Yeah, Pingjie was graduated from National Taiwan University, and then he did a PhD postdoc at the Nanyang Technology University and also in Caltech. Back to Taiwan, go to Taiwan Cheng University, suppose set up his own group. It did a lot of work for the nanophotonics, and it won a lot of awards. I saw that already when Yushan Young Scientist Award and many other young scientist award is a rising star in the field. So Pingjie, yeah, please share your screen, and we're going to hear your stories. Yeah, okay, remute yourself. Yeah, now you're mute, please.
Yeah,
Okay.
can you hear me now?
Yeah, very clearly, please.
Great. How about the screen? Can you see the screen?
Yeah, it's coming. Use. Yes, beautiful. Please.
Okay, perfect. Yeah, thanks. Yeah, thank you for the introduction. And yeah, also it's my really great honor to have this opportunity to share our recent progress about the metasurfaces and some applications based on these metasurface optics. And I also enjoy Yuanmu's talk and also look forward to Howard's talk later. And as introduced, I'm Pingjie Hu from National Tsinghua University, the Department of Photonics. So yeah, I think Yuanmu has already introduced a bit about the working principle and how we can do what we can do, what we can have from metasurfaces. So basically, I just want to use this slide to share briefly about the concept again. Basically, if now we have the nanostructures, for example, the metallic structures on top of the substrate, while the resonance, we can see both the reflectance and the phase can be modulated within the resonance wavelength range. So it has been proved that not only the amplitude phase, but also the other attributes of the EM wave, like the polarization. I think we will also talk about this, and also the phase amplitude can be modulated by using such nanostructures at the nanoscale. So before my main topics, I would like to talk about some works which have been done in our group in these years. So basically, in our group, we focus on several topics. For the first topic, we try to incorporate the active materials with passive nanostructures, or we can also utilize the active material itself as the resonators, so that we can develop some components or devices which can be utilized for active devices, which means the optical functionalities and the properties can be modulated in real time. For the second topic, we also focus on the high performance metasurface, since we nowadays are interested in utilizing the nanostructures for real world applications, which means the working efficiency is very important and plays a very important role for our nanostructure design. So this is one of the reasons why people nowadays are more interested in utilizing the high index materials like the TiO2 or silicon for the building block of the metasurface devices. But in our group, we also try to innovate some design principle which might be able to allow us to boost the working efficiency of the metallic structures, since the fabrication of the metallic structures is much easier for compared to their counterparts, that is the texture metasurfaces. So if we will be able to enhance the transmission or reflection efficiency of the metallic structures, we might be able to bring the proximity system back to the real world again. For the third topic, we also cooperate with professors in China and French In this topic, we try to incorporate the topological photonics concept with metasurfaces so that we can realize the asymmetry wavefront modulation. We also utilize the metastructures to control the quantum emissions, for example, the quantum dot or a dye, which are incoherent emissions, which means not only the coherent light source, but also the incoherent photon emissions can be modulated by using the nanostructures. And we also try to incorporate, for example, microcavity with the nanostructures so that we can control the lasing polarization in real time by rotating the device. And the last topic we focus on is to utilize the algorithm or deep learning technologies, which can allow us to design multifunctional metasurfaces for applications like beam steering or hyperspectral images. But due to the time limit for today, I will only focus on 2 topics. And the first one is regarding the tunable polarization, including by utilizing the ITO material with the passive nanostructures, and also the lasing, the microcavity for lasing applications. And for the second one is the high performance metasurface. And let's talk about the first one. Okay, so this is the schematic for our concept. In this work, basically, we try to incorporate the aluminum nanostructures as the topmost nano antenna, and incorporating with the ITO, which is utilized as the active material in this case. In between the topmost nanostructures and the back reflector, we have a dielectric spacer, so that by applying different voltage across the ITO layer, so that we can change effectively change the effective index of the ITO layer actively. And since the index of the ITO layer plays a very important role for controlling the near field coupling condition between the nanostructures on the top and the back reflector, so that we will be able to actively control the phase and amplitude of the reflective light by applying the bias between the ITO and the back reflector. So in this case, for example, if now we fix the instant polarization as the linearly white polarized, the polarization state of the reflective light can be actively switched to either X polarized or even a circular polarization. Okay, so the design principle actually is quite straightforward. The structure we utilize here is an isotropic rectangle nano antenna, as you can see here. And after the structural optimization, we can see when the instant polarization is along the X or Y axis of the nanostructures, we can see the surface proximal excitation for both cases, which happen around at a reference around 1.5 micrometer. And here show the field profile for these two plasmonic resonance mode. And once we rotate the structure by 45 degrees, then keep the instant polarization as the Y polarized. Both the surface proximal resonance mode along the long axis and the short axis can be excited simultaneously, so that we can decompose these two components into back into the X and Y axis. And by changing the applied voltage between the ITO layer and the back reflector, the amplitude and phase ratio between these two components will be modulated, so that we will be able to realize linear polarization, elliptical polarization, or circular polarization. And why we utilize the ITO material is because we can introduce the ENZ, which short for epsilon 0 region, into the optical frequencies range, so that once we change the carrier concentration within the ITO layer, which can be achieved by tuning the electrical bias between the ITO layer and the back reflector, so that we can control the effective index of the ITO layer, which means the near field coupling condition between the nanostructures and the back reflector can be modulated. And as you can see from this simulation, from these two figures, the index, the real part and the imaginary part of the dielectric function for ITO layer can be switched very dramatically across the visible and near eye region. Okay, so here show the simulation result for the amplitude and phase modulations for this device we designed. And first, we try to characterize the copolarized and cross-polarized reflection as a function of the wavelengths. You can see basically when the electrical bias changes from 0 to 12 volt, both the amplitude of X and Y components can be modulated actively. And we also analyze the phase shift between the X and Y components. And it is quite challenging to realize the linear to circular polarization convergence. To achieve the circular polarization state, basically we have to achieve a pi/2 phase difference between the X and Y components, while the amplitude ratio between these two components has to be unity, so that we determine the working efficiency based on the amplitude and phase modulation results for 1.58 micrometer. And this is the schematic for the device. We enlarge the layer of the ITO. You can see the index of the ITO layer can be modulated when the voltage is changed as a function of the spatial coordinate. And here show you the field distribution at different applied biases from 0 to 14 volt. And since from this result, you can see the ENZ region occurs when the voltage is greater than roughly 3 volt, so that you can see the field profile within the ITO layer change dramatically when the voltage is greater than 3 volt, as you can if we compare the field profile between 0 and 4 volt. And here show the summary of this Tsinghua polarization conversion using the device we designed. And this is the reflectance as a function of the voltage and also the phase difference in between, between the X and Y components. When the voltage is applied within this range from -4 to 2 volts roughly, since in this region we don't have intensity from the X Y polar components, while we have certain intensity for X polarization, so that within this region we can realize a linear cross polarization conversion. And when we increase the voltage to 12 volt or even 16 volt within this region, we can see the intensity ratio between the X and Y components is almost the same, where they possess 90-degree phase difference, so that in this region we can realize a linear to cross polarization conversion. And for the other regions, we regard them as the linear to elliptical polarization conversion. And we also try to calculate the stock parameter as a function of the applied voltage. You can see from this result, basically, the stock parameter shows agreement with the intensity and the phase difference we just discussed. We can see the polarization state of the reflective light can switch from the source hemisphere to the north hemisphere, even toward the north pole, which means we can realize a linear to circular polarization conversion. And this work, we designed the structures working in the near eye region. And next, we try to further push the working efficiency to the visible spectrum. And this work, basically, we try to embed the nanostructures within the microcavity, as you can see from this schematic. Since the structure here we design again is anisotropic, so that once we rotate the device entirely, we can see the lasing polarization can be modulated actively from a linear polarization to the circular polarization or other elliptical polarization. And the nanostructure here is patterned directly on top of the DBR mirror. And we have another fully reflecting DBR mirror on top. And the dye molecule is sandwiched also in between. And before we investigate the lasing polarization state, we first study the one-time interaction between the nanostructures and the instant light. As you can see from this schematic, we've had pattern structure directly on top of the mirror, and the instant light is expolarized. And we try to analyze the phase and amplitude difference between the X and Y components for the refractive light. So first, you can see here show you the X to X or X to Y reflection efficiency. Here you can see we can observe a dramatic change in terms of the intensity, while for the other wavelengths, which is around 532 nanometer. This is the precision where we used for the pumping source. Since we would like to utilize the nanostructures to modulate the phase and amplitude of the lasing only, so that we hope to design the structures which can only process the optical modulations at the lasing wavelengths, not the pumping wavelengths. So you can see this is the reason why the amplitude and the amplitude modulation at the black dashed line here indicate almost the same, which means it's unchanged. And we also calculate the phase difference between these two components and convert the amplitude and phase information into the stock parameter again. You can see when we structure we change the structure orientation angle from 0 to 180 degrees, all the stock parameters S1, 2, 3 are modulated dramatically. And next, we try to analyze the projection state of the laser from these integrated devices. First, we increase the laser power to ensure the emission is lasing. And next, we characterize experimentally the projection state of the lasing of the laser. And as you can see, if now, for example, we have the nanostructures oriented by 45 degree, which means the long axis of the nanostructure is has the angle of 45 degree with respect to the x-axis. You can see for this output intensity, the lasing projection state is roughly like a elliptical projection. And we also strictly integrate the lasing projection, as you can see from this result. Again, it ensures that the lasing projection state is elliptical. If now we rotate the entire device into another angle, which is 135 degree, you can see now, for example, at this wavelength, the projection state switch from an elliptical projection to a pure circular projection state, corresponding to the RCP, right-hand circular polarized light. And the spectrally integrated intensity also show a very good agreement with our prediction. And next, we try to analyze the lasing projection state on top and the bottom of the device. Since the structure here design, we assume it acts as a halfway plate, so that the lasing projection state for the toward and backward lasing direction should be opposite. So we try to experimentally characterize the projection state by measuring the stock parameter for the top output and the bottom output. You can see basically the result is opposite. And last, we try to propose a physical model for this Metasurface device. Since once the dye emission is excited, the emission oscillate back and forth inside the microcavity, so that actually the light matter interaction within the microcavity is quite complicated. So we try to propose the model to help us to further understand the physics behind this observation. So first, you can see when the pumping source is introduced into the system and the pumping projection state is expolarized, the emission from the dye molecule should be anisotropic. And since the interaction between the dye emission and the anisotropic structures is very strong within a microcavity, so that the emission intensity can be enhanced dramatically. And when the standing wave is established and the oscillation is stable, then the lasing can be realized in the far field. And we also calculate the field distribution within the microcavity for two different structural orientation, that is a 45 degree and 135 degree. You can see basically the projection standing wave is established within the microcavity. And for these two states, you can see the LCP component shows the strongest intensity, while the RCP component shows the strongest intensity for this structural orientation angle, which again agree with the previous observation. So last, we conclude for the isotropic PL emission coupled with the anisotropic nano antenna can allow us to have the specific propagation state for laser emission, while the orientation change of the entire device, which means we change the orientation of the nano antenna, we can realize the angle dependent lasing polarization state. So for the second topic, I would like to talk about the high performance metasurface. Okay, so as I just mentioned, for plasma system, basically people know very well about its advantages like the strong field enhancement and confinement. And one of the advantage in terms of the fabrication is the aspect ratio is quite low compared to electron nanoparticles, electron metasurfaces. However, the electron metasurfaces, the working efficiency is much higher than the plasma system. So here we try to realize a design principle which might be able to enhance or boost the transmission efficiency of the plasma system. And by incorporating the high transmission efficiency of the plasma system with its simple fabrication technique, we hope we can bring the plasma system back to the real-world applications again. So the idea for us to enhance the transmission efficiency for the plasma system is to incorporate the generalized Kirk condition. So for example, if now we can excite both the X-ray dipole and the magnetic dipole simultaneously in the nanostructures, we can either enhance the forward scattering or the backward scattering, so that we can enhance the transmission or the refraction intensity. And not only the fundamental modes like the X-ray and the magnetic dipoles, but also the high order modes like the quadrupoles can be utilized to satisfy the Kirk condition. And for such case, people are named as the generalized Kirk condition or generalized Kirk metasurface. And by introducing more multiples into the systems, we can not only enhance the transmission efficiency, for example, but also the directivity. Okay, and this is the schematic to describe our concept for this work. Basically, we try to incorporate not only the electric and the magnetic multiples, but also the toroidal dipoles, as you can see here, into the unit structure design, so that we can further enhance the transmission efficiency of the plasma system. And here show the schematic for the unit structures. It's a kind of the bilayer system. The topmost structure is the gold nanorod, while at the bottom we have a gold aperture, as you can see here. And after the structural optimization, you can see the transmission efficiency. The highest one we can achieve is roughly 51%. And here I want to emphasize the fabrication flow. That's because even the structural design here is double layer structures. However, we can fabricate the structure directly without involving the layer process, so that the fabrication actually is quite simple. For example, if now we have the substrate which is already prepared, then we can spin the photoresist on top of the substrate, then pattern it. Once we have the photoresist post, then we can deposit the metal directly on top of the entire device. In this case, we can see that the top and bottom structure are fabricated simultaneously. So later on, we can code in the cladding layer to match the impedance to further enhance the transmission efficiency. And here we also compare the transmission efficiency with and without the cladding layer. As you can see, the transmission efficiency dropped to less than 40% when we remove the cladding layer. And we also analyze what are the leading multiples in these structures. And basically here show the 5 leading terms, including the X-ray dipole, quadrupoles, magnetic dipole, quadrupoles, and the toroidal dipoles. Then we calculate the Kirk coefficients for linear polarization instance. You can see basically we satisfy the generalized Kirk condition. And the structure here we design is for the circular polarization convergence, so that we also verify that the phase difference between the X and Y components at the central wavelength is close to 180 degree. And later we try to reconstruct the transmission spectrum by taking all the contribution of all the multiples into account. And here show the results. You can see when we take all the contribution of all multiples into account, the reconstruct transmission match very well with the transmission spectrum directly from the S parameter. And when we remove the contribution from the toroidal dipole, you can see the transmission drop dramatically, which means the toroidal dipole indeed play a very important role in satisfying the generalized Kerr condition in our design. And since the Kerr condition is satisfied by the near-field coupling between the top and bottom structures, so that we also analyze the change of the post thickness and try to analyze what is the optimal thickness value for this system. You can see the highest transmission efficiency can only be realized within certain region of the post thickness. And we also try to compare the transmission efficiency with the texture metasurface. For example, for near R region, people are utilizing commonly with the amorphous silicon. And as you can see, for amorphous silicon metasurface in the near R region, the transmission efficiency can reach to greater than 80%. And we basically try to further boost the transmission efficiency of our nanostructures. The only difference here is that we replace the metal from with silver. You can see now we can achieve even higher transmission from 50% to almost 80%. And here show the roadmap for the transmission scheme in such a low profile proximal metasurface. For bilayer metasurface, basically we can enhance the transmission efficiency and break the limitation that is 25% for full port system. And now we can further enhance the transmission efficiency toward almost 80%. And since now we have the capability to enhance the transmission efficiency of the plasmonic nanostructures, so now we try to utilize the PP phase to realize the 2-by phase modulation and construct a meta lens by using such plasmonic unit structure. And this is the result we got in the eccentric measurement. For the central wavelengths, you can see we can observe a very black focal point at the focal plane. When we move the camera away from the focal plane, the intensity drops dramatically. And we also try to calculate, experimentally characterize the focusing efficiency for such plasmonic meta lens. You can see basically the highest focusing efficiency we can realize is approaching 50%, which is a bit lower than the transmission efficiency of the unit structures. Okay, so before ending my talk, I would like to thank my team members and also my collaborator from different universities, like Professor Cheng from Nanyang Technological University, Harry and Ruzan from Caltech, and some professors from NCKU, and also Patrice and Tsinghua for their kind helps. Okay, so this is the conclusion for my talk today. Basically, I tried to discuss and introduce 3 topics from our group. The first 2 topics are related to the projection conversion applications. By incorporating the unit structures with the active materials, we can dynamically control the projection state of either the reflective light or the lasing output. And for the second topic, we try to incorporate the contribution of the toroidal dipole to satisfy the generalized Kerr conditions so that we can further enhance the transmission efficiency of the plasmonic system. Okay, so yeah, that's it. Thanks for your attention.
Okay, great, Dr. Wu. Yeah, super nice talk and very beautiful pictures. Actually, I enjoy the talk very much. For always you see so many beautiful pictures. Okay, we can discuss later. And now we move to the third speaker. Is today we have a Harvard Day again. Yeah, I know Harvard. I can ask that 2 years ago when the Young Scientist Award, and that time I deliver a super nice talk with many beautiful fabrications, especially the circled layer of that lens. I remember very clearly. So let me introduce briefly for Professor Li. Professor Li is an associate professor at the UCI, University of California, Irvin. And it grew up in Hong Kong. I remember clearly, right? Yeah. And then it go to German, got his PhD, was in the Max Planck Institute for Science of Light. I think it's today the Nobel laureates was from this institution. Yeah. So congratulations. Okay, you on the way. Yeah. Then I got a postdoc in Caltech, and then I got effective job in US. Now he's very actively, research focus on the active linear and nonlinear quantum, plasmonic, Metasurface and zero index optics, quantum biophysics and imaging. So yeah, today, Harvard invited these two speakers to match this super nice talk is matter fiber optics. So Harvard, without further ado, okay, stage is yours. Please share the screen.
Okay, so thank you for the introductions. Let me share my screen.
Yeah. Use a present model. Harvard won a lot of award, but most kind of important one is 2021, ICANX Young Scientist Award. I have to mention that. Okay, Harvard, please.
That's great. Okay, so I think you can see my screen. So it's
Yes.
great to see you all here. So I'm Howard Lee from University of California, Irvin. So it's really my great pleasure to be here again in ICANX to really share the research. At the same time, it's really great to also discuss with great scientists like Yuanmu and also Chieh, particularly on this really exciting topic on matter optics. So today I'm going to talk about also matter optics, but trying to tell a little bit more about our research on integrating into fiber optics. So basically, integrating some of the ultra-thin optics you just mentioned in the previous two talks into fiber optic for different applications for imaging or sensing and so on. So this will be the topic I'm going to tell today. But before I go into details, maybe just let me quickly introduce myself again a little bit. So I already mentioned by Alice, I grew up in Hong Kong. Actually spent most of my time in City University of Hong Kong as my undergrad. In my last year of my undergrad, actually, I have a chance to move to Australia and Sydney to as an exchange student. So at that time, I actually have a chance to work with Ben Anderton in Kudos, which is one of the really great institutes for optics and photonics in Australia at that time. So in that year in Sydney, actually changed my life quite a lot. So because I have time to work as a undergrad student for photonics, that's also why I get passions and kind of motivation to really spend my whole life, like at least my career so far, on photonics. So definitely it's really important for me that year. But at the same time in Sydney, and actually also I met my wife there as well, definitely changed my life significantly. So my wife is from Taiwan, so that's why I always encourage students, if you have chance, let's try to go overseas to explore it. You may be able to see different university, different culture, and different people. At the same time, you may find your future career, at the same time, future spouse as well, which will be important for your life. But anyway, after my undergrad, I moved to Germany to do my postdoc in Max Planck Institute in Philip Russell Group, working on photonic crystal fiber. And then I moved to Caltech as a postdoc in Harry Edwater Group, working on Metasurface nanophotonics. And then I start my faculty position at Baylor University in Texas. I spent around 4 to 5 years there. But after that, I find I like California better. That's why I moved back to California, Irvin, around 3 years ago as an associate professor. So our group actually focusing on nano-optic, matter optics, basically everything in nanoscale, like matter interactions. We have a couple of areas working on, for example, active matter surface plasmonic active control on some of the structure, integrating the fiber optics, and still in-depth optics, which is something we also really excited on, really special material, and then quantum biophotonics, or even some of the nanophotonic circuit. So we're looking for fundamental light matter interaction in physics, but at the same time, we're also looking for different applications, potentially for imaging, sensing, or even medical or energy application. So for those of you not familiar with Irvin, actually Irvin in California, actually really close by Los Angeles, LA. So actually you're driving 145 minutes, it's not too far away. Certainly without traffic, if the traffic sometimes could be double of time. LA is actually quite bad traffic. But anyway, it's not too far away from Los Angeles, so if you have times traveling, feel free to visit at any times. And also this is the campus map here. So basically we're working with the physics department. At the same time, we have lab in the high innovation where we want to kind of having some research that could be potentially make it apply at the same time commercialize some of the research. At the same time, we're working with Beckman Laser Institute that we focusing on some of the biophotonics application. So Irvin, for those of you not know, it's a really nice city in the US, really safe, and a lot of Asian population. At the same time, a lot of attraction nearby, a lot of startup companies and so on. At the same time, we have quite a nice beach nearby the campus as well. So for example, Newport Beach, and I have 2 kids, so that's why I always enjoy the sunshine there. Certainly we are always looking for students and postdocs. So if you are interested in California, the beach, at the same time, some of our research, feel free to reach out. At the same time, we always excited to establish new collaboration and also having some visiting scientists to join our group as well. So let me tell you a little bit more about what is fiber optics. So I think many of you are really familiar with what is fiber optics. This is like a glass fiber, basically using a total internal reflectance, the core with a high reflective index. You can guiding light through the total internal reflectance. But because the glass is really low loss, that's why you can transmit for really long distance without really losing the optical signal. So that's why fiber optic have been really important for communications using this light for transmitting for really long distance with really high speed. So in my opinion, this is one of the most important innovation nowadays, because without the internet, you basically can change the life, and we cannot even watching this I can talk, or even I cannot even share the research with you so far. So that's why it's really huge impact using fiber optic for communication. That's also why the father of the fiber optic, Charlie Clark, got a Nobel Prize more than 10 years ago on his contribution using a simple physics here to apply to making significant impact for long-distance optical communication, making huge impact to our human life. So this is really important for communication, fiber optics, but at the same time, there are many other applications. For example, for imaging, you can using fiber optics endoscope for imaging inside the body, optical sensing. So for example, in my hometown, Hong Kong, the research group actually using fiber backgrading to tracking the crack in the metro wheel really precisely. At the same time, fiber laser have been really successful making different kind of fiber laser with different wavelength and so on. So all of these are really successful and also quite mature, already maybe 10, 20 years technology. But still, if you try to take a look optical fiber, you actually find they have significant limitation from the fiber optic, particularly, for example, we're using the glass material, so that's why you have a limitation on the glass material. At the same time, the geometry you need to design the fiber. For example, when you need a single mode fiber, then you need a certain geometry in order to guiding light in single mode. At the same time, once you fabricate the fiber from the fiber drawing tower, all the optical properties fixed, like for example, the phase, amplitude, polarization, or even mode profile, and so on. So at the same time, you also know, actually, there are not too many fiber drawing tower, even in the US. I think there are only a couple of them in the research institute. That means you cannot really easily design your fiber yourself using a fiber drawing fabrication. So that's why this is actually the limitation. You have limited on the optical property that can given by certain materials, certain glass and geometry here. So you may say that actually you can find easily from lab to changing the optical property from fiber. For example, there's a different component like collimator, lenses, insulator, modulator, and so on. But you can see they actually still quite bulky at the same time. Some of them are quite inefficient at the same time, also quite costly as well. So that's actually some of the things we want to see if we can find a way to change the property of the optical fiber easily as a device. So those of you who are familiar with fiber optics, you may say actually we have something called a photonic crystal fiber, microstructure fiber, developed around 20 years ago by Philip Russell. And the idea here, basically, you can actually introducing some holy structure. Basically, this hole is along the fiber so that you can using this holy structure to control the light guiding the core. For example, you can use this nanostructure, microstructure to making NSC single mode fiber, fringing fiber, hollow core fiber, or many more like a small core, highly nonlinear fiber, or even this kind of nano web, or we call this a Mercedes fiber because this looks like a Mercedes band everyone like. So you can see there are a lot of different things you can do using this microstructure. There's certainly a lot of different advantage here. Using photonic crystal fiber, for example, you can control the dispersion. You can have single mode, hollow core guiding, or even you can control the core diameter quite easily. But there's still limitation here because this is like a still making with glasses material. It's really complicated to fabricate some of this microstructure by fiber drawing tower. At the same time, you have some difficulty to reduce the losses and also setting loss. At the same time, this is like a really long piece of fiber. So we are not a simple device. So basically all the whole is along the fiber. That's why if you want to change the property, you still need a long piece of fiber in order to having some maybe highly nonlinear property or even single mode property, etc. So it's not really a small device component. But that's exactly why in my lab, we focus on this kind of so-called matter optics. We want to see if we can combine some of the nanophotonic concept or Metasurface you just heard from the previous two talks to fiber optics so that we can advancing the fiber optics to have new functionality. So you can we can combine some of the Metasurface you just heard or some of the nanophotonic structure like plasmonic nanowire, where you can actually controlling the wavefronts easily. At the same time, you can also have a strong extreme confinement using this kind of nanophotonic structure. So the idea here, basically, you can imagine, for example, we can able to making ultra thin lenses directly on the fiber to focus the light at the end phase of the fiber. So the idea here, basically, we want to make some new functionality at the same time minimizing the fiber device and component. At the same time, could be a new optical platform for looking for different physics and light matter interaction as well. So this is the goal and motivation of our research here. So that's why in my lab, we have been integrating, let's say, Metasurface on the fiber, nanowire, or even some new material called steel index material you heard briefly from Chieh and Yuanmu as well. So to using all this to changing the optical property on the fiber here. So just to highlight a little bit, for those of you not familiar with fiber optics, the fiber optics actually really small. It's like my hair dimension. So then we're actually making some small structure on the core here of the fiber. So we are really integrating really small nanophotonic matter photonic structure into a micron size photonics, which is relatively big on a dimension here. So to really change the optical property of the fiber here. So then briefly introduce you again the Metasurface. I think you'll know really well already from Yuanmu and Chieh, but basically using this kind of resonator metallic scatter, you can change the property of light using this kind of matter optics, which have been discovered like more than 10 years ago, mainly by Capazzo group from Harvard. And basically they find if you have matter structure, you can control the light in an anomalous reflection or reflection. So basically using this resonator or nano structure, you can control the phase amplitude, complex phase for reflection, and so on. But in our certainly to take a look how impressive is that. This is one really nice image from Capazzo group. We're also doing similar things as well. But on the right hand side, you can see this is the normal objective lens, like a couple of centimeter to millimeter scale. But in the Metasurface lens, again, we are talking about we can scale down 1,000 times or 10,000 times thinner lenses, while we can have similar functionality. So that's exactly why Meta Optics is so exciting, because you can scale down the device dimension while we have a similar functionality at the same time, even potentially new functionality as well. So that's why it used to mean like medium time, again, using all this structure to shaping the light in a different way. So that's why in the last couple of years, there are a lot of really exciting demonstration, but not only for lenses you can imagine this Meta Optics could be used for all the component that, as you have from Yuanmu and also Chieh, like could be a beam splitter, mirror, or even polarizer and so on. So there are many exciting demonstrations using Meta Optics, really fascinating applications. Some couple of them, for example, you can use it for voltage generation, focusing lenses you already mentioned here already, and also polarization control, or even making Metasurface hologram or camera, like really amazing talk by Yuanmu as well. So this really exciting field, but again, as I emphasize again, we actually want to integrate this Meta Optics to fiber optics to control the properties so that you may have a new functionality, like potentially spectral filtering, spinning, or even controlling the polarization, say, the phase amplitude, modulation, or even making lenses color filter and so on. So in this talk, I will focus on maybe 2 examples to tell you, making lenses and also color filter as a Meta optical fiber here. So to make lenses, you already have the basic principle, but I just try to quickly highlight again. For example, like my glasses, to focus the light, you need a certain kind of phase path difference. I have a really heavy short sight. That's why you see the thickness of my glasses is really thick. So using the thickness difference, you have a different phase difference in different path. As a result, you can focusing the light. So basically, if you try to take out the textbook to design the lenses, you need a certain phase profile depending on wavelength, radius, or even the focal length you like. You need a certain phase profile to create a lens. For example, this is a certain NA of lenses with certain focal lengths, then this is a phase profile you need. But then if you need different NA, then you just need to change the different phase profile. But in terms of the Meta Optics, basically everything is really thin. So only one thickness here. But what we do, we can using different trick. For example, one trick we can do is called a geometric phase. Basically, you have a nanostructure here. By rotating the nanostructure, you can actually control the phase at the same time, preserve a similar function efficiency here. So then that means if you need a certain phase profile, you just need a certain rotational geometry here. For this NA of lens, but for another NA, you just need to change the phase profile you need, then you need to just change the rotational geometry or distribution of your Metasurface to design different lenses here. So this is how we design on an optical fiber. And the fiber we use is using a photonic crystal fiber I mentioned to you already. So we have a holy structure on the cladding, and then we get a guiding light in the core. The reason we're using the photonic crystal fiber here because mainly because we can have a larger mole area, while preserving a single mole. So now we can have a like a 125 micron core, so that we can making more element inside the core to retrieve the phase we need of as a Metasurface. So then to fabricate this, we can, for example, coating a material we want to make, for example, a gold structure, gold layer, and then using a nano fabrication technique like a focused ion beam milling to milling the structure on top here. So then this is actually an image of my hair of the cross section. You can see the dimension and fiber optic is similar, but now we're actually making the structure in the central core here. So that means if you try to zoom in 1,000 times, you will see this structure we make. You can see all this meta structure here, and we're gradually rotating the angle from the center to the edge so that we can create a certain phase profile we need to making the lenses. But that's why at the end, then you can have a focusing lens to focus like directly at the end of the fiber. So then with this, we can characterize the Metasurface quite easily using a simple setup. So we have a tunable laser with certain polarization component here launching light into the fiber. At the end, we have a Metasurface. And then we have a camera systems here with different polarizations, say, and what we do, is move all this with a linear state so that we'll try to scan on the C direction. When you scan on the C direction, you look at the camera image, you see a certain position, you have a higher intensity. This is the focal length we are looking at on this meta lens here. So then this is some of the result. You can see basically you have this NA of lenses. You can see we have a quite consistent around 30 micron focal length for different wavelength we are interested. And then we can decide for another NA of lenses. You can see we're changing to 40 micron and also quite consistent on the focal length here, which is also matching quite well with the simulations in terms of the focal length and also the width of this focal focusing spot here. So let's give you some information, a number here. You can see the focal lengths for these lenses quite consistent throughout the telecommunication wavelength we design, and also we can making another NA of lenses here. So the efficiency here is around 15%. So it's already quite decent efficiency, but certainly we can still improve because we are using a metallic structure, using significant losses. That's why we actually design with even silicon dielectric metasurface, we're able to design, for example, achieve more than 90% efficiency here. So that's why this is quite important if you want to have a high efficient lenses on fiber. Certainly a dielectric structure could be more efficient metasurface on fiber as well. And in terms of making a metasurface, dielectric metasurface on fiber, actually there are many different ways, and this review paper actually quite nicely highlights some of the technique you can do to fabricate nanostructure on fiber. So from top down to bottom up to even material transfer. So basically you can use the typical technique like you doing nanostructure on a substrate, for example, focused ion beams like femtosecond laser, lithography, for example, photolithography, nano imprinting, e-beam lithography, and so on. So basically all the technique you use to making a planar metasurface you can potentially apply to fiber optics. But certainly it's more challenging because again, just imagine you're making nanostructure like on a hair. So all the process in terms of etchings or in terms of like really real time fabrications, you need a lot of care on that. But still, we find the lithography technique could be more applicable to making this kind of efficient metal optic fiber. For example, one technique that we find quite exciting is actually using the nano 3D printing technique. So, which actually have been pioneered recently by my friends Marcus Smith from Jena, Germany, and also Stefan Meyer from now in Mondes in Australia. So they're actually using a nanoscale 3D printer, basically nanoscribe, to printing metasurface on fiber. And the good advantage here, you can even using a high variation to even producing your metasurface, so able to making meta lenses to trapping, for example, a particle. At the same time, like e-beam lithography is still one of the really useful way to making dielectric metasurface. For example, also Marcus Submit Group, they're able to, for example, really using the e-beam lithography, making some nanostructure on the fiber. So we really think that these two techniques is still some of the really good technique to making high efficient dielectric metasurface on fiber, which is something we're also working on as well. And at the moment, I don't think anyone actually able to making a kind of metasurface or metal lens using e-beam as well, because quite a lot of fabrication challenge as well. But this is something we still kind of working on at the same time, hoping to improving the efficiency using a dielectric metasurface on fiber. So then I told you about metal lens on fiber. Let me quickly tell you also, we can making some polarization dependence element on fiber as well, using asymmetric metasurface. So now we can using different type of fiber, could be photonic crystal fiber, could be single mode fiber as well. Then we can actually making a unit cell elements so that the X and Y have a different dimension, so they can have some polarization dependence property as well. So then this is some of the structure we fabricate. You can see this is a symmetric cost on a photonic crystal fiber. This asymmetric structure with different length and also the on the X and Y direction here. And also we can making it on a single mode fiber as well. So this is the structure, but now you may not able to see the core quite easily, but we can have different trick to align the fiber so that we make sure we're actually fabricating exactly on the core of the fiber as well. So then there's some of the measurement result you can see. So symmetric structure, you see the X and Y polarization, say we have a similar transmission band here, basically color filter in certain wavelength. But then for asymmetric structure, we can turn in the color filter and basically transmitting different transmission in different wavelength here, which is matching quite well with the simulation result in terms of the spectral range and also the efficiency as well. So I told you a couple of examples using making different matter optic component on fiber, and certainly even more exciting actually if we can make it tunable as well. So potentially if you can apply voltage, as you heard from Chieh, you can be potentially changing the Metasurface property so that you can be able to tuning the focus or even scanning the beam in a real time. So this is something we're also working on, and we really think that using some of the tunable mechanism like what Chieh already mentioned, using a fluid effect dynamic, for example, using a conducting oxide material, you can changing the reflective index of the material by applying the voltage. We previously demonstrate on a panel surface, we can really making a tunable metal surface. We're really excited to able to integrate into the fiber, make it tunable as well. So certainly it is still ongoing challenge because all the fabrications or even connection will be really different, but this is something we really think could be quite exciting to explore in terms of the tunability on a metal fiber here. So with this, there's certainly many different applications you can think of using a metal optical fiber or even tunable version. One of them could be a fiber endoscope. So using a fiber, the imaging inside the body. But at the moment, if you take a look on most of the endoscope, they are still really bulky. They are in centimeter scale, and you can imagine you don't want a really thick wire sticking into your body to do all the imaging. And at the same time, you take a look on all the components, you find they have a lot of complicated optics there. Could be lenses, could be camera, or at the same time filter and so on. At the same time, you may need scanning elements or even beam splitter, etc. So that's why most of the optics inside is still bulky. At the same time, the endoscope itself is quite bulky. So you can imagine if we can reducing the size using metal optics or some of the active function as well, then you can really reducing the endoscope dimension for much better imaging and also more comfortable imaging inside the body as well. At the same time, surgery is also one big area for fiber laser surgery. Many different successful company where they use a fiber laser cutting the tissue or cancer inside the body. But at this moment, most of this kind of fiber, they are still fixed in optical property. You cannot really change the property or even the focal lengths or the focus and so on in real time. So that's something we can potentially integrate in Metasurface for one functionality. At the same time, optogenetic fiber optics using the shine light to excite the neuron, but at this moment they actually have really poor precise control of light. So that's why there could be a lot of potential even for some of the imaging or optogenetic application as well. So we really think that there could be a lot of different really exciting application using the metal version of the fiber optics for imaging or medical application, for surgery, endoscope, fiber imaging, or even trapping, or even biosensor. In terms of the communication part of it could be using for mode conversion, multiplexing, or even switching, or even coupling with some of the quantum emitter, or even using for fiber laser, or even pulse shipping and so on. So that's why we really think that a lot of really potential applications could be fine this kind of meta structure, and still at the moment it's still a initial stage of this kind of research by integrating meta optics on fiber. So I told you more about integrating Metasurface on fiber. Just in the last slide, I want to mention that our group was still working on using different new material or nanostructure to even further enhancing the fiber optics property. For example, one of the material we have been working quite a lot on is called this really exciting epson near seal material, or sometimes we call this a steel index material. So we actually can integrating them to the fiber optics or even some of the hollow holy structure, so that we can excite this kind of ENC mode at the same time potentially using for a tunable device or nonlinear device application. So at the same time in our lab, I'm also integrating, for example, plasmonic nanowire, so we can go in some tiny nanowire on a fiber, so that we can basically using the light to couple the plasmonic mode, excite the plasmonic mode, and then you can use to maybe excite the molecule and then collect in the real time. So you can use it for potentially tip enhancement using the plasmonic wire enhancement here. So these are all the things we work on. Just want to quickly summarize. So we able to integrating some of meta optics on fiber for different applications. There are a lot of really exciting potential applications for imaging, sensing, or even medical application. At the same time, we can also integrating new material, nanostructure, plasmonic structure to even further enhancing this kind of fiber optics application as well, using this nanophotonic integrations. So with this, let me acknowledge the people in my group. They are all hardworking students. Without all their hard work, I cannot tell you all the result here. Particularly the people working on this meta-optical fiber is highlighting this blue highlight here. At the same time, I want to acknowledge the funding agency on our research, including the Air Force, NSF, Moore Foundation, and also Bill Pi Innovations. With this, just want to one last advertisement. I have been working on organizing different symposium in Material Research Society. So upcoming one is a fall meeting, particularly focusing on nanophotonic metasurface and metamaterial. And there's some upcoming deadline for spring meeting in Seattle, Washington. As coming up, I think deadline is in 2 weeks. So feel free to submit and contribute. And really excited to be seeing you all in person as well. With this, let me conclude my talk and really thank you all for your attention as well.
Okay, great, Howard. Nice to see some new things. Yeah, very great talk and great, new information about this. Yeah, let's welcome everyone to join the panel discussion. Yuanmu, Pingjie, yeah, please. Okay. I think, yeah, Pingjie, could you turn on your camera? Okay. Yeah. That's great. Okay, we have 3 super talks here and 3 super, young scientists. I hope all of you have some questions for each other. Yeah, who will go first?
Yeah, maybe I can go ahead to start first. Maybe for Pingjie, so it's really exciting part and also tuning the polarization state, etc. So just want to see at the moment it's still a reflective structure in the tuning the polarization state. So do you see how we can integrate to maybe even dielectric structure, maybe even for high efficiency as well?
Yeah, to my opinion, basically, it's a kind of the trade-off process. Basically, we utilize the active material to change the optical property dynamically. So which means we need a very large index change or a very high Q factor for the resonance. Otherwise, the tunability will be very weak. Yeah, but to realize such high tunability in active materials, basically the index change has to be large, right? So which means the loss will also be very high if the index change is large. Yeah, so I would say other approach might be utilizing liquid crystal, for example, because liquid crystal is an active material as well, and it's transparent and highly transparent in visible and near regions. So probably, yeah, it could be a potential candidate for active tunable metasurfaces with high efficiency.
Thank you.
Yeah, I also have a question for Yuanmu actually. Because in your slide, one of your slides, you mentioned about the field of view can be as large as 80 degrees, if I remember the number correctly. But from your talk, I'm not quite sure about the design of the unit structures, because we usually the the performance of the metal lens can be very, can be degraded when the incident angle is large. So sometimes we can even see the aberrations or coma effect. So I'm just curious about in your design, how could you avoid such aberration issues, or how could you achieve such large angle field of view?
Okay, actually, that's a very, very important and very good question, right? So as we work on metasurfaces for imaging application, one of the major problems is that once the incident angle is off normal, right, then you have this very strong coma aberration, right? So actually, over the past few years, there have been a lot of work trying to address this issue. One of the approaches to try to use, for example, the a bilayer structure, such that you can try to correct this coma aberration. I believe one of the work in by Professor Andrew Farrand's group. And also, there has been other work trying to, for example, putting a aperture, a small aperture, in front of this metal lens in order to reduce. Basically, you can try to give a different phase profile for different angle incidence. And another approach recently have been proposed is to use something called a. Let me try to remember this. I think it's just basically. I think it's something called a hyperbolic phase. So basically, typically we that's probably not a good term. Like how do we say this? Basically, you can redesign this phase profile in order to try to somewhat to sacrifice the quality of the point square function, but you can still get a better field of view. But in our case, actually, in order to get this 80-degree field of view, so we took basically another approach that once we found that basically a metasurface cannot really do very well at off-angle incidence, so we decided to design a hybrid device that is made of a refractive and a diffractive system. So that can help improve this field of view.
Yeah, but which means you will also somehow increase the size of the entire system a bit, right?
Okay, yes, that's true. But in some cases, or in a lot of cases, I guess people don't really care, because if you think about these, for example, a smartphone camera that's made of 5 or 6 pieces of lenses, but that's still actually quite small or compact, right?
Yeah, agree.
Yeah.
Okay, thank you.
Yeah,
and
that's a very good, important question. Yeah.
Thank you. Yeah, so sorry, I also have a question for Howard. Yeah, I'm also curious about, do you think it is also possible to, I think it is possible, I'm not quite sure how to really realize such concept, to control, for example, not only the polarization, but also the angular momentum of photons in fibers. I'm not sure, is there any specific applications for such device?
Yeah, I think definitely. So I think still a lot of potential we can try, even different nanostructure or different fiber types. So I think there are some research people actually using the OAM mode for long distance communication. So they have special fiber they can actually guiding an OAM mode as well. So, but how to converge those modes easily by normal fiber coupling to those fiber with is actually still challenging, also not that efficient. So there's some kind of meta components you can easily to convert some of the mode, even some of the OAM mode pressure. I think that could be some exciting area as well. But yeah, I think still at the moment it's still not completely discovered so far.
I see. So once we carry some information like the polarization information of photons through the interface of the fiber and the free space, then would the information be lost when the photon or light are guided inside the fiber? Would the polarization state will be decomposed when the light is propagated in the fiber?
Yeah, so that will be depend. So yeah, there are different type of fiber can, for example, preserving certain polarization state as well. So then, yeah, I think it's really depending on what kind of stage you're looking at. For example, as I say, there's some OAM fiber that can serve certain kind of OAM mode for quite long distance as well. So I think that is still a lot of potential we can do. At the same time, even nowadays, like quantum optics or emission, etc., is quite a hot topic. But how can we actually potentially enhancing some of the emissions, let's say from a single emitter or even directly coupled to a fiber, single photon source to a fiber? That could be something still potentially exciting, potentially using the metasurface to maybe enhancing the emission at the same time enhancing some of the coupling. So I think that, that's still quite exciting area. But I think at the moment still most of the metasurface on fiber is still potentially it's not that efficient. That's why I think still making more efficient dielectric metasurface is still some area to work on as well.
Yeah, I see. Thank you.
Right,
Okay,
so
maybe I have a question. Okay, to Harvard. Yeah, Harvard, I saw you use, fabrications like lithography, all this work quite often to make the structures, so I have a question is for the substrate. So normally, what kind of, materials, you use and what kind of, advanced materials you want to use?
Yeah, so most of the initial demonstration we was using the metals. So because we can more easy to fabricate, so we can imagine basically a fiber with coating the metal on top, then using focus ion beam is easier way to kind of destroy the structure to make a metasurface on top. But as I mentioned, so focus ion beam you cannot really make dielectric metasurface because you can't really milling, for example, silicon structure or some other titanium oxide material. So that's why different technique will be necessary. And certainly we want a low loss material, for example, could be a titanium oxide, silicon structure on top of fiber. But again, the challenging things again is like you're basically doing everything the same, but now your substrate is not a fast substrate anymore. You actually have a fiber optics. So then you need to coating the material, coating polymer. At the same time, you may need to spin coating, get a uniform coating on top. Then you need to move it to a lithography, e-beam lithography device to making the structure on top, and then you need to do other development or etching at the end. So that's why it's making more a little bit more challenging in terms of fabrication. At the same time, how do you align really well to the core of the fiber? It's also something challenging. And then if you want to even make it tunable, how do you connect to the metasurface on a fiber like a hair? It's also some research is still ongoing. So that's why I think the goal is still making low loss material on fiber as a metasurface, but at the same time, if we can add in some functionality, that will be really exciting as well. But we are still not there yet, so we still kind of ongoing research on that. Yeah.
Now you study not only metal surface, also metal materials.
Yeah. So.
Right. I guess I also have questions for both of you. So I guess I'll start with ours, because we were just discussing about this fiber integrated metasurface, right? So one of the things I don't quite understand is that so for fiber, I from what I understand is that it should have a finite numerical aperture, right? So when that incident on the metallus, it's not a collimated beam incident on the metallus, right? That should have a lot of finite incident angles. So how does that translate to your metasurface design?
Yeah, so that's also one of the limitation because you have certain dimension you have in a optical fiber. For example, single mode you only have a couple of microns. So, but that's why in some of the fiber, let's say photonic crystal fiber, you can making the core size bigger so they can have an aperture bigger. At the same time, you can also do some other tricks. You can even expanding the beam first, and then you can have a metasurface to collimate the beam at the end. At the same time, then if you want to focus or speeding the light, you can have another metasurface to do that. So, but that will be some trade-off depending on what kind of aperture size or what kind of lens size you need. You may still need to decide what kind of size of the metasurface you want to have. But to say that, still, like if you look at the endoscope, so we have all sort of this kind of problem already. So you need to have a really small dimension lenses, etc., for imaging, etc. But now the Metasurface provide you some opportunity to reducing the thickness and size at the same time, some new functionality that could not be produced by normal lenses on fiber. So that, yeah, I think that's just the part that we kind of thinking could be some opportunity there. Is that answering to your questions? Like,
yeah, of course. All right. Okay, thank you. And I have another question. I think maybe it's for PG, but as for both of you, because you two are both, I think, pioneers for using ITOs, right, to doing this tunable Metasurface, for example, to do this beam steering. And I see right now there are some companies such as Samsung are working on using this ITO to make tunable Metasurface for LiDAR application, right? So I guess Howard, your first question has already asked Pinji about this, about the loss of ITO. But one thing I don't quite understand is that if according to this some of these I don't know this coupled mode theory that if you want to get a very good phase shift from this ITO integrated Metasurface, you really have to pass through this something so-called this critical coupling condition. Then however you minimize the loss of this material, okay, at this critical coupling condition, the reflection can still be zero. So I don't know if that's an intrinsic problem that cannot be solved, or is there any way out? Because I think the loss issue is still there for application.
Yeah, to my opinion, I think, yeah, as I mentioned, yeah, I think it's a kind of the intrinsic property or intrinsic problem we would have definitely when we utilize such material. To my opinion, I'm not quite sure. Yeah, but and one thing I might concern for ITO is it's also very difficult to control the intrinsic concentration density while it is fabricated. So, for example, even all the conditions we use are the same, but the property of the material, I mean, the ITO could be very different once it is deposited. Yeah, this is another issue, and which means if the optical property once it is fabricated is different, which means the index of the material itself is different. So how to control the material properties to make it much more stable and even make the loss lower, yeah, I think it is really very challenging. Yeah, to my opinion, I'm not quite sure about Howard's opinion.
Yeah, I can comment a little bit on that as well. So I think in terms of the minimums, let's say reflectance you mentioned, so potentially you can also offset a little bit, so you're not really working on a minimum of the reflectance dips that can enhance certain efficiency, but still maybe not go to the 90%. So I think this is still something is still ongoing as well, but potentially you can couple to some of the maybe boundary of continuum structure combined with the ITO. That could be something potentially have a high transmissive tunable Metasurface. But again, I think it's no one demonstrated so far, so I think still some questions on that. But in terms of the reproducible material from Pinche, I think it's really depend. For example, we actually are making the ACO with ALD, so we're actually able to control really well reproducing the same material. So I think as long as you have a dedicated chamber, let's say just for us, we are using mainly, for example, ACO without other material contamination, etc., then you can still control quite precisely what kind of NK or what kind of ENC wavelength we are looking at. So yeah. And maybe talking about the company, so I have a question on Yuanmu. So it seems like you have a company on some of this polarization camera. So just want to see, could you tell me, for example, what's the cost? Is that easy to make reducing the cost significantly using the Metasurface structure and so on, or anything you can share about?
All right, so about that, so first thing I wanted to mention is that from our experience, so for Metasurface, if we can later mass produce it using, for example, either deep UV lithography or nano printing, the cost of the Metasurface itself can be close to zero. What I mean is that, for example, for each, let's say, an 8-inch or a 12-inch wafer, you can cut, let's say, thousands of Metasurface at once. Right, so if you think about the price, the cost of the Metasurface itself, it can be down to not zero, but less than $1 or $2. That's certainly doable. So then when we talk about cost of this 3D camera itself, okay, then we're not trying to reduce the loss by replacing the Metasurface replacing the refractive lens with a Metasurface. We're actually trying to basically replace those laser scanners and all those very expensive detectors, and to use a monocular camera for 3D sensing. I think in terms of cost, that's a cost benefit there. Yeah. And for Metasurface itself, as I mentioned, so I mean the fabrication of Metasurface itself, to a large extent, it's very similar to a diffractive optical element. So if you see that right now in your iPhone, right? So people are putting there are several pieces of diffractive optical element there already, right? They're manufacturing that in TSMC, right? So I guess it can be very cheap. Yeah, there is no problem there.
Like really exciting, huh?
Oh, yes, it is. Okay, yeah, thanks for all of you. This wonderful, questions. Maybe I'm going to ask some questions because today everyone knows that we have a big news is for the Nobel laureates for the physics going to, 3 scientists for the experimental development, about the atom second laser pulse or light pulse. Yeah, so this is a big news, and everyone was excited. Now it sounds have a big future for the people who is doing experimental for the challenging, experimentals. Yeah, I think Yuanmu just say that you have done some work in this field. Yeah, could you show us something about this?
Yeah. Maybe I can just talk a little bit about this. So I think this year's Nobel Prize in Physics was actually it was given to this auto-second science, right? So basically, it can make people. It's been given for people for their contribution to make very short pulses of light. That is 10 on the order of less than 10 to the minus 15, right? This less than a femtosecond pulse, right? So for our work, we have been working on kind of a little bit to try to generate those very short pulses using a process called a high harmonic generation. Okay, because if you think about if you want to make very short later pulses, so a single cycle of a optical wave at, let's say, a wavelength of 800 nanometers, that can already be like a 2 to 3 femtosecond. It's impossible to make an attosecond pulse of it. So you have to use some very extreme nonlinear optical effect in order to achieve, for example, a coherent light source into the deep or extreme UV or into the X-ray band. So I think there, I mean, one of the opportunity, as we have been talking about meta optics here today, right? So I think all these nanostructures may have this potential even to further help the development of a better, let's say, attosecond source. That's something I think is quite interesting. And in general, I feel like this is, I guess, for the entire field of Nobel Prize. So optics has actually got recently there has been a lot of Nobel Prize related to optics, right? So that's really a huge encouragement to all of us working in this area. So we're all excited about this story, and just share it with all my graduate students, and I hope that'll encourage them to stay in this field.
Okay, great. So how about Pingjie? Yeah. So will we wake up next year for waiting for the call from somewhere?
Yeah, yeah. I'm not quite very now. I don't know very much about the ultra fast laser. Usually, yeah, not like Yuanmu. Actually, I try to utilize the ultra fast laser for some measurements only. Yeah, but yeah, as Yuanmu just mentioned, basically this year's Nobel Prize are given to excuse me. Yeah, many scientists who are working working in laser or optoelectronics. Yeah, even like a few years ago, we have the blue LED or other
Trap pulse, like
yeah. So yeah, we I think we hope the students or our colleague can see this good news, and also the students can be inspired from these Nobel Prizes and see, sometimes students, they don't know very well about the knowledge or the technologies. They know things when news come to the world, like the Nobel Prize.
Yes.
So yeah, when they saw this, I hope they can also be inspired by this and to seek more opportunities for researchers. Yeah, not only for getting job in industries.
Yes, yes, it is. Yeah. So Howard, you may be very excited about this. Yeah.
yeah, definitely. So yeah, I mean, we're dealing with nano optic metasurface, but like light source is really important as well. It's like nowadays we can making much shorter pulse and I mean higher energy at the same time. You can looking for different electron dynamic, for example. We also do a little bit on nonlinear optics like Yuanmu on some of the epsilon ESL material. So how can we enhance things in nonlinearity or even how's the nonlinear electron dynamic will look like some of this really extreme laser or really short pulse laser could actually enhance a lot of different fundamental studies. So that's why it's really exciting to hear about this news as well. But at the same time, I think I second everyone's as well. I think optics is really exciting field. So I think in the last 20 years, I think more than 10 Nobel Prize actually related to optics as well. So, and also a couple of years ago, a lady Nobel Prize winner on the trap pulse as well. So all are really exciting. So that's why if you are not working on optics, I encourage you to go to the optics field, and at the same time, you may able to get a Nobel Prize in the future. So we are still a young researcher relatively, so we're really looking for like I don't think any Nobel Prize on the metamaterials or nanophotonic field so far. We're looking for maybe more famous scientists will be able to get a Nobel Prize in this area as well. So we will see someone at some point maybe Yuanmu and Chieh as well. Yeah.
Yes, young scientists have more opportunities because till now you can think about the most challenging, kind of work in the in the in this photonics field. That will be big future in the maybe the next 20 years. You will get the call. Okay, yeah. So I also have another question I can ask is very popularly. I want to hear that Harvard, like you say that you got a bachelor degree at Hong Kong, then got an internship or some it's an internship, right? Yeah, go to Sydney and you got to change your life and change your future, and then you travel all over the world to get a job. So I mean, for your experience, what kind of the lessons are the best part you can share with the students who is listen to this talk, yeah, they still have more opportunities, to go somewhere to have a magic like you are, because now recently you see the world is changing, right? Now many people was worried about that if they can go somewhere freely or something like that. Can you give some words to the young generation?
Definitely. So I really think that like I think if you have the opportunity, really try to explore it. So I think that's just some recommendation. So especially be open minds because like again, you don't know your future, so only when you step outside, find the opportunity, you will change your life. And for example, like definitely, I don't even imagine I was able to do photonics before I moved outside to Sydney. So that's something really definitely changed my life. And again, it's like at the beginning, I don't even speak English. I mean, we learn English in Hong Kong, but I can't really communicate in English at that time. So, and also when I met my wife, I don't even speak Mandarin. So we're speaking with English. So my Mandarin is learning after that. So again, it's like I think what you need is for students is just to find the opportunity, really try to open mind to go there to explore it. I think that's what I always encourage. But in terms of for example, in the US, we always still really welcomes a lot of overseas students as well. For example, in my opinion, I really like to have Asian Chinese student as well in my group. So that's why we always still open up opportunity, and we actually still have a lot of different students coming from different part in Asia as well. For example, I have a new PhD from Taiwan and also China as well. So we are still actually having students coming, but certainly there's maybe some limitation. Maybe you're afraid the visa is reducing the number of visa reducing in the US, but this is really hard to say. So I think as soon as you get in, it's like the future is hard to predict, and after a couple of years, maybe everything will change at the same time. It's not difficult to find opportunity in the US. I think there are a lot of opportunity in the US in terms of research, in terms of your future career. So I think that is something I still really encourage everyone to explore and apply as well.
Okay, I have additional questions. Howard, are you safe there? So because many people think it's now very safe in US, there's many bad news.
Yeah, definitely. So yeah, we still really safe. So I would say also Irvin is one of the safest place in the US. Like I need to advertise a little bit. So we have the best Asians community here. So basically, you see all the kid here are Asians. So it's really safe. Like, but certainly there are some city maybe less safe in the US, but this is the same for all the countries. So I don't see any issue at all. Like as Asians working in the US. So definitely, don't worry about the safety just yet. So yeah.
Okay, nice you clarify that. Okay, so Pinjie, yeah, can you have few words for, you have trained in Taiwan, then you go to overseas to, US for postdoc and back to Taiwan. So can you give some words for what kind of, experience or special, feelings you gain when you do postdoc and Caltech that time?
Yeah, I also want to echo Howard's opinion. Like, yeah, try to keep your mind open always. Also I actually got my PhD in Taiwan, in Taipei actually. So like what Howard just mentioned, when I was in Taiwan, I also learned English in Taiwan, but I didn't have the capability to communicate with foreigners very well. When I was in Taiwan, yeah, we only know how to, pass the exam and read the words, but we don't know how to really use these languages to, English is a language. So the most important thing for us to utilize such language to communicate with each other and exchange the experience and knowledge also. So yeah, I have to say I was very fortunate to have the opportunity to have postdoc overseas, like from Singapore to Caltech in the US. I even had an experience as an exchange student when I was the PhD student. I visited University of Southampton in the UK. So that's my actually first time to stay overseas for more than 3 months. Yeah, and yeah, when I was in the other countries, I have to say I can really learn different things from different countries, the people from different countries, and not only the things how they learn things, but also the cultures. It's really important, and we can only see the things and news from YouTube or even your laptop, but now you can have the opportunity to interact with people in person. Yeah, and like this is also very important, like what we are doing now. Since the pandemic issues, we are very used to use the virtual meetings, but still people miss the on-site meetings because we thought it's very important to have the interaction with people in person on site. Yeah, the feeling is very, very different. So keep your mind open and try everything you can do. And even, of course, sometimes you might fail, but don't worry about that. Life is very long. You are still young. So nothing to be afraid. So just try your best to get everything you want and pursue your dream. So
Great.
yeah.
Great. So Yuanmu, yeah, how did you feel about this? Yeah. You mute? Yuanmu, you mute. Yeah. Oh.
Sorry. So for me, I think going abroad for a PhD study was probably the best decision I've ever made in my entire career. So that I think going to the US for a PhD study really helped me a lot in terms of shaping my entire career or my life. I also met my wife there, and also have very nice mentors both for PhDs and postdocs. Actually, right now I'm a undergraduate mentor for roughly 50 undergraduate students here in Tsinghua. So I'm in Chinese, I guess it's called 班主任, right? So actually, at this moment, they're in their junior year, about to pass, going to their senior year. Okay. Over the last summer, actually, 6 students from my class actually they decided to do this summer research abroad, and both in the United States, and some of them actually go to Hong Kong. So I really encourage everybody to, as Howard and Pinji said, I really encourage people to go outside, right? So I think the best way to learn and to improve yourself is really to step out of your comfort zone. And also, as Alice has mentioned, that right now we have this geopolitical tension between different countries, and I think the best way to actually to relieve all these tensions is really to have people to talk to each other, right? And to communicate with each other. And once you start to communicate with each other, you may find that the other people on the other side of the ocean may not be the devil as you might thought about. Right? So people can all be friends, I guess.
Great. Yeah, actually, I can add is one of the best education platform, Yeah. So, and since we started this at COVID-19, I think I talk with the whole world. Yeah, that's exactly the feeling that Pinji tell us. Once you open the mind, actually the whole world, the different cultures will open the mind for you. Yeah, you can understand each other. You can get, different kind of friend, and also can get different support. Yeah, all the people's there. When you know each other, talk to each other, the things was changed. And you also learn a lot. The most benefit is you learn a lot, from the overseas, the different cultures. Yeah, thank you all of you for this great, talks and discussions. Yeah, let me share my screen, okay. Yeah, I have a special gift for you to see this. Yeah, I can ask. Normally we have this special certifications for our speakers. So Yuanmu, yeah, this is for you. Yeah, thank you very much for your talk.
Okay, thank you, Alice.
Yeah. So, Pinji, yeah, this is for you. I will send the electrical version to you by email. Okay. Yeah. Once I met you, I will deliver to you face to face.
Thank you. Okay. My pleasure to deliver talks. Yeah.
Yeah, Howard. Yeah, this is for you. Yeah, we continue for this, and proud to tell all of you that today we also, even it's a holiday, we have 15,000 people online. Yeah,
Wow.
we're very popular, talks, and thanks for your contribution. Next week we're going to have a talk is for MEMS, the biosensors, and the energy harvesting. So our three speakers from different part of the world, UK, China, and Japan. And we also have, the panelists to discuss about this next Tuesday. Welcome to join us. And thank you all of you for this wonderful talks, and keep on going, for follow your talks. Okay, thank you.
Thank
Thank
you.
you. Bye bye.
OK，谢谢，拜拜，再见。
拜拜，谢谢。
OK， yeah, bye.
Bye.
Harvard, you can go back to Harvard.
不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can。你也能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的